Okay, so our next unit is going to be finishing off the chapter 3 that we started at the beginning of last unit. So we have already done sections 3.1 and 3.2, and then we went on to chapter 4. So now we're back doing the remaining sections in chapter 3. And chapter 3, if you recall, was titled Factors and Products. So section 3.3 is on common factors of polynomials, but before we get into that, we're going to do a little bit of review on distributive property. So if you remember from junior high, distributive property is basically when you have a term outside of brackets where you'd have a sum or difference of terms inside those brackets, and you can basically eliminate the brackets by distributing that term outside to each term inside the brackets. And it's basically distributive property, multiplication over addition or subtraction. So let's review with a few examples. Okay, so the first one there is 2 outside of 3x plus 5. So I'll show the steps for this one, but I might not show them for all of them. So this would be 2 would get distributed to the 3x and then to the 5. So we'd have 2 times 3x plus 2 times 5. And that would give you 6x plus 10. So you can skip this first step if you want, and just go, if you can do that in your head, and just go to the second step. So like for example, the next one here would be 4x times 2x. So we'll skip the first step, and that would be 8x squared, a result of 8x squared. And then 4x times negative 6 would be negative 24x. And then this one, negative 3x times 5x is going to be negative 15x squared. And then negative 3x times a negative 2 is going to be plus 6x. All right, so factoring using the GCF is kind of working backwards from what we just did. But before we do that, we need to just go over a couple of things. We're going to do a little bit of demonstration with algebra tiles, not a whole lot, but factoring polynomials is like basically the inverse of multiplying polynomials. And some of these factoring techniques can be modeled using algebra tiles. So in this workbook, shaded tiles are going to represent positive and white tiles are going to represent the negatives. So when we're looking for to factor a polynomial, the first thing you should always look for, first rule of factoring is always check for a GCF first. Okay, so you can probably highlight this step here now. So the initial step when factoring is to look for the greatest common factor. This is a very important step. It can help make the remaining factoring easy if there is more factoring to be done. All right, so we're going to take a look at some examples. So if we have a polynomial 6x minus 9, using algebra tiles, the long rectangular tiles represent the x's. So we would need 6 of those, and they would need to be shaded because it's a positive 6x. And then we would need 9 white square tiles because they represent the units of 1. So the white would be the negative. So 9 of those and 6 of the rectangular tiles, if we put them together in a rectangle, as shown here in the diagram, you can see the length and width of that rectangle would represent your factors, I guess, that would give you 6x minus 9. So these two things would have an area, if you want to think of it that way, of 6x minus 9. And when we look at the dimensions of the rectangle, they would be what your two factors of 6x minus 9. So 6x minus 9, according to this, would have factors 3 outside of 2x minus 3. And if you just quickly check using the distributive property, you can see that if you remultiply the 3 inside the brackets there, you would get 6x minus 9. All right, so we're going to take a look at some more examples. And algebra tiles aren't always, easy to have on hand, so we will learn how to do it algebraically and just kind of demonstrate a few examples with algebra tiles as well. So the first one, we have 3x minus 9, so that would mean we need 3 shaded rectangle tiles and 9 small square white tiles. And when we arrange those, we can form a rectangle as shown in the diagram here. And if you look at the dimensions of that rectangle, this would be 1, 2, 3 short little lengths, I guess, which are about the size of the unit tiles. So this would be, you're just looking at the dimension on the side here. Those are short, small dimensions like the square tiles. So this would represent 3, and it would be positive because it's shaded. And then if you look at the other dimension along here, you would have one long dimension, which is the length of what we consider to be x, and it's a positive. And then we have 3 short, but they're white, so that's negative. So that would be x minus 3. So the factored form would be 3 outside of x minus 3. And the GCF would be the greatest common factor. If you look at this here and this here, the greatest common factor of both of those terms would be a common factor of 3. And that shows up outside of your factored form here. If you have x squared plus 4x, that would mean you need one big square tile for x squared, and then 4 rectangular tiles. And you can arrange those in a rectangle as shown in this diagram here. And the dimensions would be, on this side here, it's a long dimension, so that's represented as positive x. And here, along this side, you would have a long dimension, which is positive x, because it's shaded, and then shorts, 1, 2, 3, 4 shorts, and they would be represented as units, so x plus 4. So therefore the factored form, the factors that multiply to give you x squared plus 4x would be x times x plus 4. And the GCF, if you look at each of these terms here, the greatest thing that's common to both of those would be an x, and that is represented by the number out front here. That's the greatest common factor, would have been taken out algebraically. We'll do a little bit more practice algebraically on the next page. All right, so sometimes working with algebra tiles might be a little bit tricky or inconvenient because you can't really represent, or it's too hard to represent the polynomial that you have with algebra tiles. And sometimes when you try to arrange the tiles, you cannot form a rectangle. But you can have a GCF of a polynomial represented with algebra tiles. Sometimes, if it can't be represented in a rectangular format, can it be split up into equal groups of the same types of tiles? So for example, in negative 2x squared plus 6, when we take the tiles that are too big, the large squares representing the negative x squareds, 2 of those, and then we need 6 positive tiles, so 6 shaded tiles. You can try to arrange those whatever way you like, but you're never going to be able to form a full filled-in rectangle. However, you can split them up into 2 equal groups of negative x squared. Each group has a negative x squared plus a 3. So there would be, factored form would be 2 groups of negative x squared plus 3. In terms of the GCF algebraically, if you look at this here, if you look at each term, the only factor that both of those terms have in common would be a 2. And then if you take x squared, negative 2x squared, divide out the 2, you'd be left with negative x squared. And if you take the 6 and divide out the 2, you'd be left with plus 3. So that's how you do it algebraically. However, most times when we are doing it algebraically, even if there isn't a negative in both terms, but the first term in your polynomial expression has a negative, normally people will take that negative out. So it'd be negative 2 outside of. If you take the negative 2, divide it out of the first term, you'd be left with x squared. And if you divide it out of the 6, you'd be left with minus 3. So normally, if the leading term is a negative, that comes out as a GCF. It won't show up like that in algebra tiles, but algebraically, that's typically the way that most people would write it. And that's what I have here, the notes at the top here. Most times when you're factoring algebraically using GCF, the negative will be factored out with the GCF if the first term is negative, even when the other terms. So this one would be, as we just did, negative 2 would come out, and you'd be left with x squared, and 6 divided by negative 2 would be negative 3. And you can double check if you redistribute the negative 2, you will get negative 2x squared plus 6, if you multiply it out. All right, so let's just practice using the GCF, using the algebraic method, because sometimes, like I said, especially if you look at B, we wouldn't be able to represent B in the examples below with algebra tiles, because we don't have tiles to represent x squared and y fifth term. All right, so let's take a look at these examples. And you should remember that when you're factoring, you basically should take out the greatest common factor. So that means that what's left inside should have no other factor common to it other than plus or minus 1. All right, so the first one, if you look at each term individually, you've got a 3x and you've got a 12, or minus 12. Both of those are divisible by 3. So 3 would be our biggest factor that goes into 3 and 12. They don't both have a variable, so we have to leave the x inside. So the 3 would come out, and the first term, if you divide out the 3, you'd be left with x. And the second term, if you divide out the 3, you'd be left with 4. And you can double check if I remultiply the 3 times the first term, I get 3x. If I remultiply the 3 times the negative 4, I get negative 12. So I will get what I started with back if I multiply. And if you look inside, there are no other common factors to the x and the negative 4, so that's done. The next one, if you look at each term, if you look at the numbers that go with each term, there is no common factor for 5, 6, or 8, negative 8. If we look at the x's, so all 3 terms have an x power of x in there, and the one that's common to all 3 would be x squared. And if you look at the y's, the one that's common to all y's, because all 3 terms have a y, power of y, and the one that's in all 3 of them would be y cubed. So then you start taking that term and dividing it out of each of the terms. So if I take the 5x squared, and I'm kind of thinking, if it helps you from what we did, that's why we did chapter 4 first with the exponents. When you have 5x squared over y5 divided by x squared y cubed, you can see that you're going to be left with a 5. If you divide that out, the x squareds are going to cancel out, and the y cubed is going to cancel part of the y's to the fifth. There'll be still a y squared left. So that's kind of what you're doing each time. You're figuring out what's left inside the brackets. So in the next one, when you kind of imagine 6x cubed y fourth over x squared y cubed, you would be left with a 6, and you've got an x squared that would cancel out two of the x's with the x cubed, leaving you with just an x, and then the y cubed would cancel out, leaving you with just a y. And then the last term, you'd have a minus 8. And if you take out that x squared, you'd be left with x to the 4. And if you take out the y cubed, it's gone. So basically, you would have just negative 8x to the 4. And again, if you look at the terms left inside the brackets, none of those have anything in common that would be able to take out, so that you have taken out the greatest common factor. All right, the next example, if you look at each of the 3 terms, the coefficient of each of those terms, each of those has a common factor of 3, I think is the biggest number that goes into 15, 12, negative 12, and 18. So I'm going to take that 3 out. Whoops, I didn't mean to put a bracket there yet, because I want to take out some x's too. All right, so 3, and if you look at the x terms, each of these terms has an x term in it, and the one that would be common to all 3 would be the lowest power, x squared. And then you would take each term, 15, right, I can imagine kind of you're doing this, 15x to the 4 over 3x squared. So then that means 3 goes into 15 5 times, and then the x squared would cancel out 2 of the x's in the top, leaving you with just x squared. And then minus, same kind of thing if you do the next term, negative 12 x cubed over 3x squared is what you're kind of thinking. So that's minus 4, and you'd have an x left. And the last one, 18x squared over the 3x squared. The x squareds are going to cancel, and 3 goes into 18 6 times. So that would be your factoring of that. And again, the terms left inside have nothing in common, so that means you've taken out the greatest common factor. Okay, so let's try a few examples here now to see if you can factor using either algebra tiles or the GCF method, using the algebraic method. So the first one there, you've got the expression 3x squared plus 6x plus 6 represented using all positive algebra tiles. There are 3 large squares to represent the 3x squared. There are 6 rectangles to represent the 6x, and then there are 6 unit squares to represent the 6, the constant term 6. So when we look at that, they are already arranged into equal groups. So, and there are 3 equal groups. So our factoring for that would be 3 equal groups of x squared plus 2x plus 2. Right? Because that would be x squared. Each group has x squared plus 2x plus 2, and x squared plus 2x's plus 2 units. All right, so the next example, we're going to use, not going to use algebra tiles, we're going to try to do it algebraically. So we look at each of the terms in the expression and see if we can take out the biggest factor, the common factor, biggest common factor for each of those. So in the number parts, the coefficients and constant, 2, 6, and 10 all have a factor of 2 that's common. And there isn't an x in all 3 terms, so we can't take out any of the x's. So that looks like it's the biggest common factor, or the largest common factor that we can, that those 3 terms have in common. So that would be 2x squared, divide out the 2, you'd be left with x squared. Negative 6x divided out the 2 would be minus 3x. And 10 divided by 2 would be 5. And just double checked inside the brackets there, the terms inside the brackets, x squared minus 3x and 5 have nothing in common, so 2 is the greatest common factor. And if you check the next term, again, you've got constant, a linear term, and a squared term. So when you look at each of those, they don't all have x's, but there is a common factor of 5 that goes into 10, and the coefficients of negative 5 and negative 5. So I would take out the 5, and I would be 10 divided by 5 would be a 2, minus an x for the next term, and then there minus, if you take the 5 out, you still have an x squared left, minus x squared. And question C just kind of talks about the, and I already mentioned this above when we were doing the algebraic way. In question C, you've got a expression 5x squared y to the 5th minus 20x to the 7th y squared. And it says, why wouldn't you be able to use algebra tiles to help you factor that? And the reason would be that there aren't algebra tiles that represent x squared y 5th term, right? So you only have algebra tiles for x squared, x, and constants. No algebra tiles exist for this term to represent. Okay. All right, so our last page here just does a little bit of practice, and we're going to practice the algebraic way, because we don't always have algebra tiles in our back pocket to try to factor. So first example there, if you look at the 2 terms, the common term to both of those would be a 3. And what would be left inside, 3g, to take out the 3, you'd be left with a g, and 6 divide out the 3, you'd be left with a 2. In B, if you look at each term individually, 8 and 12 have a common factor of 4. That would be the greatest common factor for 8 and 12. And both of those terms have a d, but d would be the greatest common factor. So that means 8d divide out the 4t, you'd be left d, so you'd be left with 2. And then 12d squared divide out the 4d. 12 divided by 4 is 3. And then the d taken out of the d squared, you'd still be left with a d. And the next one, if you look at the 3 terms, they don't all have variables in them, but they all have a common factor. 6, 12, and 18 all have a common factor of 6. So 6 divided by 6 would be 1. Minus 12 divided by 6 would be 2, and you still have the z there. And then 18 divided by 6 would be the 3, and you still have the z squared. And the next one, if you look at each of those terms, in the coefficient part, 3 and 6, 3 is GCF of 3 and 6, x squared and x would be the GCF, and y squared and y squared, well, y squared could come out because it's common to both. So then if you compare the first term, divide out your GCF that you took out, you'd still be left with an x, because the 3 would be gone, the y squared has been taken out, and there'd still be just one x left. And then minus the 6xy squared, divide out 3xy squared, would just be a 2, because the x would be out and the y squared has come out. Just move those up. Okay, so the next example, if we look at each of those terms there, x squared is common to both of those terms, and you'd be left with a 3x squared plus x squared divided by itself will be left with plus 1. And in F, if you look at negative 20, negative 30, and negative 25, negative for sure can come out, and I think 5 would be the biggest factor that goes into all three of those numbers. And C is in all three of them. And there's a D squared, and a D, so D can definitely come out. And then you'd be left with negative 20C to the 4D, divide by the negative 5CD, so that would be positive 4, because negative 20 divided by negative 5 would be positive 4. If you take out one of the C's, you still have C cubed left, and the D is out. So then you move to the next term, and it's going to be a plus, because you've taken the negative 5 out, so it's going to be 6. Negative 30 divided by negative 5 is 6. You've taken one of the C's out, so there's still a C squared left. And you've taken one of the D's out, so there's still a D left. And then the last term, you've taken the negative out, and 25 divided by 5 is 5, so it's going to be plus 5. And you've taken the C and the D out, so that's done. And in G, we look at both of those terms, 4 and 30, the coefficient part. 2 would be the GCF of those numbers. You've got G's in both terms, and G, the smallest power, would have to come out. There aren't K's in both of them, so K cannot come out as a GCF, but there are P's in both of them, and the smaller power would have to come out, because P squared would be in both, P squared and P to the 5. So then when you compare, you've got 4G cubed K P squared divided by the 2 GP squared, so 4 divided by 2 is 2. G cubed, if you take out the G, you still got G squared left, and the P squared has come out. In the second term, 30 divided by 2 is 15, and then you've taken out the G, and you've taken out P squared, so there's still a P cubed left. And the last example, 12 and 20 and 28, 4 would go into all three of those. You've got x only in the first two terms, you don't have an x in the last term, so therefore you can't take the x out, but there is a y in all three terms. So then if you take the first term, divide out the 4y, you'd be left with 3 and the x squared, and the y is already out. In the next term, it would be a 5 and an x left, the y is already out. And the last term would be a minus 7, 28 divided by 4. So then, or negative 28 divided by 4. So then, and the y comes out. So there's some questions on pages 155 and 156 of your text now that you can try to practice some of the techniques we've learned in this section.